In today's world, electricity is considered to be the life and blood of a nation's economy. Growing demand for energy resources is a crucial issue worldwide today, especially in developing nations like India. India is known to have a heterogeneous mix of energy resources that include both non-renewable resources like coal, petroleum and gas, and renewable resources like solar, wind and hydroelectric power. Current studies suggest that we presently use an optimal mix of all the available energy resources to barely meet our needs. In the coming years, the energy requirement of India is expected to reach about 800 gigawatt by 2032 and 1300 gigawatt by 2050. It is obvious that there is an urgent need to explore novel methods of generating clean and safe energy. In this context, nuclear energy has been voted for as a highly viable option. While coal continues to be the major electricity source in India, it is indeed a matter of great pride that about 2% of the electricity generated in India now is based on nuclear energy. India today is the owner of robust nuclear power technologies, engaging in R&D in various aspects of atomic energy and nuclear engineering, including exploration and mining of uranium, nuclear energy development and implementation, application of radioisotopes, etc. This growth has been achieved by the relentless efforts of numerous researchers under the guidance of visionary leaders. The efforts to make our country self-reliant in energy production started right after the independence. While the oppressing British rule left the country in shambles, the increasing population and rising industries demanded more power. Initially, coal and hydro were considered as the primary energy sources. Fossil fuels like coal are limited and hydro capacity was bound. Hence, the country was looking for an energy resource that would ensure that we would be self-reliant in energy for centuries to come. 60 years ago, nuclear technology was a futuristic technology. No one in the world had yet constructed or operated a commercial nuclear power plant.
Today, we have a realization in the country in all levels that nuclear energy is a very important component of the energy mix that we need for the country, because there is a pressure on fossil fuels. We know that they cannot be there for too long a time. There is a question of cost of the fossil fuel. There is a question of environmental issues connected with fossil fuel use, like carbon dioxide released to the environment, etc. So, looking at all this, the country knows that nuclear energy is very important.
The first ever commercial nuclear power plant was set up by the Soviet Union and became operational only on June 27, 1954. It produced just 5 megawatts of electric power. For a young nation eager to modernize and leap into 21st century, nuclear power was one of the options. In this context, the setting up of the Atomic Energy Commission in 1948, followed by the establishment of the Department of Atomic Energy in 1954 to implement the policies framed by the Atomic Energy Commission, are important historical milestones. While India was striving to emerge as a nuclear power nation, there was a catch. Uranium was not widely available in India. It was at this juncture that Homi Jahangir Bhabha, the first Secretary of the Department of Atomic Energy, made a visionary proposal. He saw potential where no one else saw a worth. The monazite sand present in the beaches of Kerala and southern Tamil Nadu are naturally rich in the rare element thorium. India has very little uranium reserves but possesses around 30% of global thorium reserves. Thorium in those days had no use, but Bhabha realized if only the mildly radioactive thorium could be made into a nuclear fuel, an energy source would be found ensuring energy security. Naturally occurring thorium itself is not a fissile material, but can be converted into its fissile isotope of uranium, namely uranium-233, through transmutation in a reactor fueled by other fissile materials. Thus emerged the three-step Indian nuclear program. This sequential three-stage program is based on a closed fuel cycle where the spent fuel of one stage is reprocessed to produce fuel for the next stage. Alpha particles cannot transmute thorium into U-233. Only neutrons can. We need plutonium for use in fast breeder reactors where the surplus neutrons can convert thorium to U-233. In the first stage of the Indian three-stage nuclear program, natural uranium is used as the fuel. The nuclear reactor produces plutonium as a byproduct. If we can harvest plutonium from the first stage reactors, it can be used as fuel in the second stage breeder reactors. Plutonium produced in nuclear reactors is a mixture of various isotopes including Pu-239. It also contains Pu-240 and smaller quantities of Pu-241, Pu-242 and Pu-238. Thus, we should not give the impression that Pu-239 is being separated.
In what is called a thermal reactor, which is basically a moderated reactor, we call either moderated with water or heavy water. What happens is the neutrons which are released out of fission, they have very high energy and they are immediately slowed down by the moderator. So, that is required to increase the probability of fission in the next chain. Whereas, in a fast reactor, the neutrons are not moderated. The neutrons are specifically maintained at a higher with higher energy, but the probability of fission comes down. So, the reactor core will be enriched in fissile material. And the advantage of fast neutron is that such a reactor is capable of producing more fissile material than what it consumes. So, that is why the term fast breeder. So, breeding is a process in which we generate more fuel than what we consume. So, if you take for instance, if I load 1 kilogram of fuel in a fast reactor, at the end of what is called a doubling time, the 1 kilogram fuel would have burnt, but it would have generated 2 kilograms of fuel. So, the extra 1 kilogram can be used for building another reactor. So, that is called breeding. The advantage, or I will say the necessity for breeding is like this. Natural uranium contains only 0.7% of what is called uranium-235. It means that if I take 1 ton of natural uranium, only around 7 kilograms of fuel is burnt in a thermal reactor. The remaining 993 kilogram is uranium-238, which is not burnt. So, by putting this U-238 with some plutonium and burning in a fast reactor, I am able to convert this U-238 slowly into plutonium and will be able to completely burn away the uranium-238. So, it is a very efficient way of using the natural uranium reserves of the country.
The second stage of the Indian nuclear program consists of fast breeder reactors. In these reactors, the fuel contains plutonium. Thorium can be used in the blanket which surrounds the core. The fission reaction in fast breeder reactors helps in the conversion or transmutation of thorium into uranium-233. Neutrons produced in fission are absorbed by thorium and thorium becomes fissile uranium-233. Thus, the fast reactor not only produces energy but also additional fuel. That is why it is called as breeder reactor. It was way back in 1985 that a test fast breeder reactor was established at the Indira Gandhi Nuclear Research Center facility at Kalapakkam near Chennai. 40 megawatt thermal capacity test FBR was established to master all the dimensions of the fast breeder reactor technology. The fast breeder test reactor FBTR uses an indigenous mix of 70% plutonium carbide and 30% uranium carbide as fuel. India was thus the 7th nation to have the technology to build and operate a breeder reactor after United States, UK, France, Japan, Germany and Russia.
Our center is dedicated to development of fast reactor technology. We commissioned the FBTR fast breeder test reactor in 1985. We have been operating it for now 38 years and we have had an excellent experience with the FBTR. It has operated very safely, barring a very few minor incidents, I should say, which have provided us some good lessons. But other than that, I should say it's a world class performance. This reactor has used a fuel which is we call it as a carbide fuel, which has not been used anywhere in the world as a driver fuel for a reactor. It has been tested, but it has not been used as a driver fuel anywhere in the world. But with that kind of a fuel, we have had excellent performance. In fact, we have been able to extract a very high quantum of energy from the fuel. It is usually expressed in terms of what we call as burn up. Burn up is nothing but how much energy you can extract from a given quantity of fuel. With the fuel in FBTR, we have been able to reach a burn up level of 165,000 megawatt days from 1 ton. This is supposed to be exceedingly high figure. It shows a good level of performance, which means that we are able to design the fuel, we are able to fabricate it indigenously, we are able to have it safe operation. We have knowledge on all aspects of fast reactors today.
Based on the lessons learnt and experience gained from construction and operation of FBTR, the Indian atomic energy scientists have gained confidence to launch the design and construction of a 500 megawatt prototype fast breeder reactor at Kalapakkam. The reactor at IGCAR is called FBTR and not as Test Fast Breeder Reactor. The first commercial prototype fast breeder reactor with 500 megawatt electrical capacity is under construction in the premises of Bhavini at Kalapakkam in Tamil Nadu. It will be functional by the next year. The PFBR is designed to make use of MOX fuel, a mixture of plutonium dioxide and uranium dioxide, and is expected to have an operational life of 40 years.
As you know, we have been operating a fast breeder test reactor in Kalapakkam since 1985 or so. And that experience has given us a lot of confidence to design the new reactor, prototype fast breeder reactor. Our industry has been groomed to develop a special components and systems. And now we are almost completing the construction of prototype fast breeder reactor. The nuclear fuel for that is already being supplied from Tarapur by our advanced fuel fabrication facility of EARC. I expect that sometime later this year, we will be getting into the criticality of this important reactor for us.
The Bharatiya Nabhikiya Vidyut Nigam Limited, that is Bhavini, is a public sector undertaking that has been set up to construct and operate fast breeder reactors in the country. Based on the fast breeder reactor technology developed by the scientists of the Indira Gandhi Center for Atomic Research. About 98% of the components and materials used in this reactor have been developed indigenously by the Indian industry, researchers and the scientists. The completion and operation of this reactor will take the Indian nuclear program into higher orbit.
This reactor has not only a specialty that it has plutonium and sodium, it has specialty of using the materials which have not been experienced in the country in the past. Tolerances which has not been any time achieved or tried. Dimensions very giant, very big. Handling, transportation, erection, tolerances and methods to be developed for the first time. For all practical purposes to say, all the knowledge which was there can only be partially used and everything has to be developed afresh for this technology.
In the PFBR, Uranium plutonium mixed oxide will be used as the fuel and the coolant shall be sodium. The heat generated during the process of fission in the core of the power plant will be absorbed by the primary liquid sodium. The primary sodium will transfer the heat to the secondary sodium. The secondary sodium loop will be used to carry the heat to the steam generators. The steam produced in this manner will finally be used to turn the turbines and generate electricity. This steam can again be condensed with the help of the seawater and can be used again. It is pertinent to note that in the fast breeder test reactor in operation for 30 years, there has been no reported abnormal radioactivity release or radioactive contamination during the reactor operation history.
In this place, Bhavni, the company, has been formed to make fast reactor. They work on a different neutron spectrum as far as safety is concerned. This is a very clean reactor. One of the cleanest reactors which are there, they are fast reactor. Radiation release is almost insignificant. Dose given to the operating and maintenance crew is almost nil. You can just walk through and you don't get any dose. You do major maintenance, you don't get any dose. This is exceedingly clean reactor.
Nevertheless, scientists do not want to take chances and are taking steps for ensuring strict safety standards. In this regard, various safety standards and measures have been designed to meet all possible kinds of emergencies. The advantages of nuclear energy so produced are going to be many. First and foremost, while nuclear energy is more powerful and efficient than other alternative energy sources, the production process does not emit any greenhouse gases and pollute the environment. Unlike traditional sources of energy like solar and wind, which require sun or wind to produce electricity, nuclear energy can be produced from nuclear power plants even in the case of rough weather conditions. They can produce power 24/7 and need to be shut down for refueling and maintenance purposes only. Nuclear energy is also an affordable option. While the setting up cost of nuclear power plants is relatively high, the cost of fuel and running cost is very low. Also, small amounts of fuel can produce large amounts of energy. Hence, the transportation of the fuel is easier than fossil fuels. As a result, the overall cost of electricity production is low, making the electricity cheaper for the public. While reserves of coal, oil and natural gas are limited and expected to vanish soon, nuclear resources are currently widely available and expected to last for several hundred years. Today, India leads the world in fast breeder technology. While Russia also has fast breeder reactors in operation, other countries are expected to exploit this technology only around 2025 and beyond. We should not point to Korea in isolation. India plans to complete 3 500 megawatt fast breeder reactors by the year 2020. With setting up of a fleet of fast reactors, the stage 2 of the nuclear program will attain maturity and help to produce enough U-233 from thorium to launch the stage 3 of the nuclear program. The 3-stage nuclear power program would contribute to self-sufficiency in energy and for energy security of India for centuries to come.
And this reactor has come out so well, almost a temple of excellence, and is demonstrator of the capabilities which Indian industries and Indian researchers and Indian youth has got.